Greetings everyone. As always, I would like to start with a brief disclaimer. These videos are meant to help people learn physics. At times, it's meant to provide helpful hints, and at other times, it's meant to take you through the entire problem with hopefully what is a decent explanation so you can solve many others on your own. I try my best not to show the entire answer in any one screen so that the video remains about learning how to solve the problem and is not something simple that can be used as a shortcut to cheat or get ahead. If you're putting up with the sound of my voice, clearly you must want to learn this material. Okay, let's get started.
Okay, let's do this. So this is believe it or not, this is a really fun problem, I think, once you get used to the physics of it. It's bringing together a lot of concepts. So two balls, they're right next to each other. You can see them here. They start off like this, and then somebody pulls ball A to the side, and they let it go. And that's where our problem gets started. So first of all, it asks what is the velocity of the lighter ball, which is ball A is lighter than ball B because ball A is 40 grams and ball B is 60 grams. So they're asking what is the velocity of ball A before impact. Well, so we haven't gotten into collision, so just before impact it's a simple quotient that somebody lifted it up and they dropped it down. That should give it some speed. What would that be? So this is using the concept of how to put this. Step one is the concept of potential energy converting into kinetic energy. So the ball is given some potential energy because you took it against gravity and you release it, and then it gets some kinetic energy thanks to the potential energy of gravity. So let's think about that first, right? How much energy did we put into the ball? So what's the potential energy due to gravitation? The formula for that is simple: mass times acceleration due to gravity times the displacement in the. So let's translate this a little bit. Mass times the constant for gravity is g, 9.81 meters per second square. We'll come back to that, and you don't have to write d. You can also think of it as a change in the y direction. So that notation should also work for some people. So yeah, how much potential energy did we give to this system is the quotient. And actually what we don't know is the y. I don't think we know the y. What we do know is that this string is 30 centimeters, just like the ball A and B, they both have the same string. And they're right next to each other, so I guess it's more of an assumption. And if this is 30 centimeters, then really the quotient is, and this is 60 degrees, what is y? So I guess before we can find the potential energy we give it, we need to find how much did we displace it against gravity. It's not this is not the displacement against gravity, only this directly against gravity is the displacement against gravity, and that's the stored potential energy. So to find the change in y, we use just regular diagrams. So here we go. So the ball was here, it went here, it was 30 centimeters here, and it's 30 centimeters here. The length of string doesn't change, but if you draw a line across and you say, okay, this is 90 degree, this is 60 degrees, it's given to us, then what's this thing right here, right? And if you remember SOHCAHTOA, which is a mnemonic, you'd say, okay, sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, tangent equals opposite over adjacent. Here what we're looking for is a side that's actually adjacent to the 60 degree angle, right? It's right next to it. So we want to use either this formula or this formula. We don't have a value for the opposite, we don't have a value for the adjacent, so this probably doesn't make sense. We do have a value for the angle, so cosine of 60 is equal to adjacent, which is, we know it's 30 centimeters over hypotenuse. And well, actually no, we don't know adjacent, that's what we're trying to find, my mistake. We know the hypotenuse is 30. right? So now there's only one unknown, and if you solve for the adjacent side, that's cosine of 60 times 30, and the thing that I'm calling adjacent is just basically change in y, or change in the displacement, or the change in y, however you want to call it. You can convert it into meters from centimeters. That's generally a good idea. So if we do that, we can, this is centimeters, and we multiply by cosine of 60, 0.3, that's in meters, and with that, adjacent or y or displacement, all the same thing, comes out to 0.15 meters. Okay, great. So now we know what the displacement is, so we can go on with life. It is 40 grams is 0.04 kilograms multiplied by gravity, which is 9.81 meters per second squared times 0.15, right? Great. So now we know the potential energy, or if you don't want to do this, you can just use 10 if you want to use nice round numbers, and you'll end up with, this is your potential energy, 0.06 joules. So when you lifted the ball to the side, this is how much energy you gave it. Now it's potential energy, and you release the ball, and just before collision, it's going to have a certain kinetic energy. And the law of, so this was, let's say this was step 1. Well, actually finding y was step 1, right? And then finding the potential energy was sort of step 2. So what would be step 3? Well, use the conservation of energy. So, potential energy at the top should be the same as kinetic energy at the bottom, right? Energy can neither be created nor destroyed, it can only be transformed. So here we are, and there hasn't been a collision yet, so it doesn't matter about elastic or inelastic. The system hasn't changed. So we know the potential energy at top was this much. I'm skipping units for now, and we know that formula for kinetic energy is 1/2 mv squared. If you don't know that, you can take some time to memorize these basics. And we were asked about the velocity of the ball before impact. So this is great. You solve this, and you kind of end up with something like square root of 3 and 1.7 meters per second, and that's fine and dandy, right? We've answered part A quite easily. Now part B is saying, well, what's the velocity of the two balls after the collision? And the collision is elastic, meaning both conservation of energy and linear momentum apply. Again, you just kind of throw what you know on paper, right? So what do you know about linear momentum? We know linear momentum before and after should be the same. So linear momentum of ball, initial of ball A plus linear momentum initial of ball B should be the same as, I'm guessing they don't move together, so should be equal to final of A plus linear momentum final of B. So just go with that, and this is mass times velocity initial of A plus mass times velocity initial of B, mass times velocity final of A plus mass times velocity final of B, right? And the mass of A and B does not change before the collision or after the collision. So there's no initial or final corresponding to that. So 0.4, just substitute, and we just found the velocity, initial velocity of ball A was right here, 1.7, plus, I guess, ball B wasn't moving, so it's 0. 0 multiplied by mass is also 0. So we get that to be 0 initially. Now after the collision, they'll both move, so it's something like 0.4 velocity final of A plus, sorry, it's not it's 0.04. Yeah, 0.04 and 0.06 time velocity final of B. And that's our equation, and I always find it useful because I know what the velocity of ball A is. It's kind of a neat trick. You're going to see what happens shortly. It works both ways, but I always try to solve for the unknown ball velocity. Well, let's see what happens. So we could write this equation in terms of f of A, or we could write it in terms of f of B. I'm going to choose to write it in terms of f of b. So if you solve for it, it's something as simple as, I don't know, 1 point, let's say, 13 minus 0 0.0, no, 667. Yeah, you can solve for it. I may not be right about this, so feel free to do the math on your own, but the physics should be sound here. Final velocity of ball B. Okay, and wait, no, this is not right, is it? Let me think about this. Yeah, final velocity of ball B. That makes sense. So if you solve the equation and you divide, you should end up with something like this. Anyway, so now you've defined the velocity of final ball B in terms of velocity, A, that's what I meant to write, in terms of final velocity of ball A. So we can substitute this somewhere. But where would we possibly have the opportunity to substitute that? This was step 4, by the way. Okay, that's kind of tricky. 2 unknowns, can't solve that. So let's come up with step 5. There's the conservation of linear momentum, there's conservation of energy. After all, it is an elastic collision. So same thing, kinetic energy before is equal to kinetic energy after. I stands for initial, F stands for final. A, B, right? 1/2 mv squared is the formula, and you start working on it, and we all actually know this. This was 0.06. We solved for this in step 3 or step 2 really. It's the same as the potential energy. So there's that. Ball B wasn't moving, so that's going to be 0. 1/2 mv squared. V is 0, so the entire equation is 0. And here we go. So we say 1/2 0.04 mass times velocity squared, and this is where things get a little tricky or ugly, however you want to look at it. Final velocity of ball A squared plus, let's zoom in a little bit so I can finish writing this, 1/2 mv squared, so mass is 0.6 over 2 1/2 mv final velocity of ball B squared. Yeah, okay. Now you just substitute. You know that, hey, I know what this is, final velocity. If I put this here, my entire equation will be in terms of just one variable, which is final velocity of ball A. And then it's a ugly quadratic equation, or beautiful if you're a student of math and you love this stuff. And we just solve for it. So I guess it ends up looking something like this. If you're just comparing notes and you're messing up the math, I guess this could be useful. Ball A plus, let's see, if you solve for it, 2 and 0.06, you end up with 0.03, and you have F final velocity B squared, right? That's what you want, or better yet, just write it outside. So you substitute this and you get something, oh my gosh, so much fun, right? 0.667, and V, now it's in term of A, and this is squared, V plus, and everything here is the same. This symbol means same as above, if you're not used to it. And this is, if you have never seen this before or don't remember, is equal to A squared plus B squared minus 2AB. Also, so this equals that plus 0.03, and then you do all this craziness and you end up with 1.3 plus, that's A squared. B squared will give you something like 0.44 VFA squared now, plus, and minus 2AB will give you something like minus, I don't know, 1.5 V final of A. And you still have to multiply everything by 0.03, so this is fun, right? Everything stays the same, and then you end up with something like, let me write this one down, 02 V F of A squared, And now you have plus 0.039 plus 0.013 VF of A squared minus 0.045 VF of A, just multiplied by 0.03 here, everything. And you know, these two can be added together. Long story short, you keep solving for this, you're gonna end up with something like, I did the math already, and I hope you will too. 0.045 V final of A minus 0.021, and you know, 0 on one side, and this has the makings of a quadratic equation with A, B, and C, and you can just say, oh, I'm going to solve for VF of A by using this quadratic equation, which you may not remember. If you don't, unfortunately or fortunately, you should commit this to memory and become a better student at both math and physics. And when you solve it, the fun thing is you'll end up with this you'll end up with two answers. One of the answers will be 1.7 and the other answer will be negative 0.36. And here's the cool thing, this answer, this is for velocity, final velocity of ball A, right? And the fun part is, hey, technically, guess what? We had, before ball A hit the collision, it was actually at 1.7 meters per second. So the math is able to see beyond all the words that we humans use and tell us, hey, one of the speeds for this ball should be 1.7 meters per second squared. It's able to see that. And we know that's the pre-collision speed. And the math just gets it, right? The formula just understands it as if it was magic. But that's how math works. It's fact-based, right? And so then this is what we're looking for. This is the post-collision speed, final speed of ball A. So this is what we want to go with. And once you know this, you plug it into your equation here, right? And you get the final velocity of ball B also. And, you know, that will be the end of that. You just plug it in there and get your answer. All right. Best of luck. Oh no, wait, I almost forgot. I'm not done yet. This problem asks about not just about the velocity of each ball after the collision. There's a part C. What will be the maximum height of each ball, right? They're on a string. So, you know, they strike each other and they get a certain speed, but that speed is going to push them up. What speed will that be? So, you know, if you solve for final velocity of ball B, which is, and if I get the math wrong here, that's okay. You guys can use the physics and fix the math. Sorry, that was a bit sexist, wasn't it? You folks can. All the people out there can, guys and girls and men and women, and can use this to fix it themselves to get the right answer. So yeah, final velocity of ball B would come out to be something like 1.4 meters per second. Also. So now you have, so let's do part C. And in part C, they ask us how high will the final displacement of ball AB, and how high will the final displacement of ball B be? And we go back to potential energy and kinetic energy because we know the velocity. So we say, hey, I know mass times gravity, change in y. So let's solve for ball A first, okay? 1/2 mv square of ball A, final velocity of ball A, and final displacement of ball A. Mass goes away, don't have to deal with that. And just, so you have final velocity of A, and you just move g to the other side, and you know, so it becomes v of final of A squared divided by 2g, and you just substitute and get that. And similarly, surprise, surprise, for final displacement of ball B, you can say, oh, what's the final speed of ball B squared divided by 2g, because you'll go through the same motions and you will have an answer, and it will be something like, you know, it'll just be a number in meters, be something, and whatever you calculate, you know, as long as you plug in the numbers into the calculator correctly, you'll be fine. It'll be something like, in this case, it'll be negative 0.36 squared, right? I love math. It gets it right. 2g, if you take g to be 10, then you're sitting on top of 20 here, and so you get a positive displacement because the strings are stuck to a ball. The balls have to go up, so the math gets it, even if we humans take some time to understand it. And that's a value in meters, so meters, and this is 1.4 squared, right? Meters per second, right? 0.36 for ball B, and you divide it by, again, 2g, and if g is 10 meters per second, just because you didn't want to use 9.81 and you wanted to have a nice and easy life, then that will also come out to something in meters, and that will be answer. Okay, I hope you feel confident with the principles of linear momentum, just your basic SOHCAHTOA rule, how to apply it. You understand that displacement when measuring potential energy doesn't have to do with the arc, but has to do with the direct linear y dimension changes, and you can feel comfortable using both kinetic energy and linear momentum equations, and finding a substitution, and then using that in a quadratic situation to solve the quadratic, and then laughing at how easy it really is to take one speed and ignore it because that was the speed before collision. Like magic, the math knows it, that was the speed before collision, and you know what the right answer is. Then you get the right answer for ball B, and from there you again use the kinetic energy and potential energy conservation to find the new potential energies, and therefore the new heights for ball A and ball B, and that's all there is to it.